Now, you're probably wondering, why is there a tomato and a carrot on my screen right now? Well, I want to ask you, what are the defining characteristics of a tomato and a carrot? Now, you're probably going to say that the defining characteristics of a tomato and a carrot are their colors. A tomato, of course, is bright red, and a carrot has a reddish orange color. Well, where do these colors come from? And the answer to that question is simple: alkenes. To be specific, the alkene lycopene gives the tomato this bright red color, and the alkene beta-carotene gives this carrot its reddish orange color. So, moving on. In this video lesson, we will be discussing alkenes, and by the end of the video, you should be familiar with the properties of alkenes, the rules for naming alkenes using the proper AUPAC naming system, drawing alkenes given a structural formula, geometric isomers, and the different kinds of reactions involving alkenes. But also, you should know at least one cool fact about alkenes by the end of the video. Alkene properties. So, alkenes are unsaturated hydrocarbons, and they must contain at least one carbon-carbon double bond. The base molecular formula of an alkene is C subscript N, H subscript 2N. This just means that for every one carbon, there are going to be two hydrogens. Alkenes are more reactive than alkanes and are soluble in nonpolar solvents. Alkenes have a lower density, melting point, and boiling point than alkanes, and this is because of weaker forces and double bonds being present. And remember, the shape around the carbon-carbon double bond is trigonal planar. Alright, so moving on. The naming is almost the same as the naming for alkanes. The prefixes indicating the number of carbons present is the exact same. The only difference is in the suffix, which instead of "ane" is "ene" to indicate, the double bond. If more than one double bond exists, then the ending is changed. So, for example, if there's two double bonds, the ending will be diene. If there are three, then it'll be triene. If there are four, then tetraene. The letter A is added after the prefix, and then you will add one of these suffixes depending on how many double bonds are present. So here's a little example. So from this we can see that there's seven carbons, and there are two double bonds and located at carbon 1 and carbon 4. The A is just there to separate the two consonants, so the T and the D. Yeah. Also, just to go back to quickly review the prefixes. Remember, for one carbon is meth, 2 is eth, 3 is prop, 4 is but, 5 is pent, 6 is hex, 7 is hept, 8 is oct, 9 is non, and 10 is dec. Alright, so moving on to some practice problems. Alright, so I'm going to go over the rules quickly. So the first thing you need to do when naming alkenes is find the longest carbon chain. So this chain must include your double bond, your carbon-carbon double bond, and this chain will not be your parent chain. So you have to make sure that the carbon-carbon double bond has the lowest possible number. Let's highlight this right over here. Find any substituents and just write them down so you know. And then at the end, just simply put your equation together. So I'm going to try with the following. You see there's 6 carbons here. 1, 2, 3, 4, 5, and 6. Well, we know what the parent chain is, but I'll just highlight it anyways. There you go. And let me just quickly number this. So it's going to be 1, 2, 3, 4, 5, and 6. Alright, so we want our carbon-carbon double bond to have the lowest possible number. So it makes sense for us to start from the left. So 1, 2, 3, 4, 5, 6. There's 6 carbons, so we know the prefix is going to be hex, and then there's double bond, so ene. So it'll just be hexene. Hexene. Oh, looks a little janky, but that's fine. You can write it as 1 hexene as well, which is the same thing. The reason you don't include the 1 is because it's just assumed to be 1 when it's not written. So you have one hexene or just hexene here. Moving on to the next example. So to identify the parent chain, we need to look for the chain with the most amount of carbons. Get my highlighter out. And 1, 2, 3, 4, 5. 1, 2, 3, 4. I think we should start from left to right, the numbering, so we can give our carbon the double bond the lowest number possible. And the longest chain includes 5 carbons, so we know it's going to be pent. Switch over to my pen really quick and number this. Alright, 1, 2, 3, 4, 5. Alright, now we also have a substituent. It's a methyl group, and let me just highlight that as well. So this right over here is our substituent, and this is at carbon 3. So we know now that we must write our substituent. So it's methyl on the 3rd carbon, so it'll be 3 methyl. 3 methyl. Now we also know that there's 5 carbons in the parent chain, so it's going to be pent, and our double bond is on carbon 2, so it'll be 3 methyl, 2 pentene. There we go. Alright, moving on. So now we're going to be given the names. So we have pentene here, and we have 3-methyl-2-octene, and we must draw them. Now drawing is pretty simple. So we know that there's pentene, so there's 5 carbons. So 1, 2, 3, 4, and 5. There's 5 carbons. Now the pentene is going to be on the 1st carbon since there is no other number specified. So it'll just be plop, and there we go. 1, 2, 3, 4, and 5, and we have a double bond on the first one. So this is good to go. 3-methyl-2-octene. Look at the oct. 8 carbons. So 1, 2, 3, 4, 5, 6, 7, and 8. Now I just want to let you know that I'm making line diagrams. Of course, you can make structural diagrams. I would recommend making them both, which makes for some great practice. But I'll be making line diagrams because, I'm an expert. So we have 8 carbons, and we have a methyl group on the 3rd, and our double bond on the 2nd. So 1, 2, so we have our double bond here. 1, 2, and we have our methyl group on the 3rd one right over here. Now let's double check. 1, 2, 3, 4, 5, 6, 7, 8. Yes, octene. Yep. Double bond number 2. Yes. Methyl on the 3rd. Yes. Perfect. Moving on. Alright, now we're going to get into multiple double bonds, which we did touch upon earlier on in the video. And, once again, very, very simple. Just count the carbons. So 1, 2, 3, and 4. Let me number it down. 2, 3, and 4. Now let's identify where our double bonds are. So we have a double bond on carbon 1 and a double bond on carbon 3. So pretty much what this means is we're going to write 1 and 3. Also, if I started numbering this way, it would have been the exact same. 1, 2, 3, 4, right? But I just started from left to right. So we know that there's 4 carbons, so it's going to be bute. 1, 3, bute. Now remember, since we have 2 double bonds, our ending is going to be diene. Now T is a consonant, so we must add an A so it doesn't sound weird. So we have an A. Now we're writing diene. Diene. Alright, let's double check. So there's 4 carbons. Yep, we got bute. There's 2 double bonds. Yep, diene. And they're located at the 1st and 3rd carbon. Check. Moving on. Now this one's not as complicated as it looks. Once again, same steps. Count out your carbon. Actually, I'm gonna mark down our parent chain first. So our parent chain will be, here's our parent chain. Yep. This is our parent chain. This is the longest carbon chain, and it also covers all of our double bonds. So perfect. Now what we need to identify is where do we start counting from? to give our double bonds the lowest possible numbers. So let's start counting from the left. 1, 2, 3, 4, 5, 6, 7, 8, 9. So if you count from the left, our double bonds will be at 3, 6, and 9. If you count from the right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it'll be at 1, 4, and 7. So right to left actually give us the lowest set of numbers. So that is what we're going to be doing from right to left. Now we also have a methyl group. Let me mark that down really quick with a highlighter. So this is our methyl group. And this is located at carbon, I believe, 6. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Alright, so we have a methyl group at 6, carbon 6. 1, 2, 3, 4, 5, 6. Yep. So remember, same steps as this one. Where are our double bonds located? So we have 1, and then we have 4, and then we have 7. Remember, there's a comma between the numbers. Now we also have a substituent, a methyl group. So in this case, the methyl group will actually precede our double bonds. So this is located at carbon 6. So simple, 6, methyl, methyl. Let's just separate it. So 6 methyl, 1, 4, 7. We have 10 right over here. We have 10 carbons, so it'll be dec. And then remember, we need to add in the A right over here. And now we have, how many double bonds do we have? 1, 2, and 3. So it'll be decatriene. Decatriene. Let's just double check. So 6 methyl, yep. Methyl at carbon 6. 1, 4, 7, decatriene. 10, yeah, we have 10 carbons. 1, 4, 7, yep, check. Triene, yep, we have the A in there. Yep, perfect. Moving on. Geometric isomers. Very, very straightforward. Very, 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 very easy. Once again, just, if it helps you out, mark down your parent chain. Boom. Remember, these hydrogens, it's the same as saying CH2, double bond to another CH2, but just to show you the geometric isomers, it's written in this way. So, as you can see, let me just get my pen out really quick. Get a little red color. So, as you can see, our the largest molecules that we have are the CH3s, and they're both on the same side. Now, when they're both on the same side, this is called cis. So let me just quickly write it out. Pen right there. So this is called cis, meaning on the same side. Cis. So this shows us that the heaviest, the largest molecules, my bad, are on the same side. Now everything else is the exact same. We have 4 carbons, so it'll be bute. Our double bond is located on the second carbon. It doesn't matter which way we start numbering, from left or right, it'll be at the second. So it'll be cis to butene. So we have C4H8 here. Oh, whoops. Now, here's another example, but this is with trans. So here's a trans configuration. Here, let's highlight our parent chain. It's right over here. Remember these hydrogens once again. CH, sorry. Let's take a little peek here. Let's get our pen right over here. Sorry, this is a CH actually. Yeah, CH. But now if you look here, remember these are on the same side. Now what's happening is the largest molecules we have here, the CH3s, are not on the same side. They're actually on opposite sides of each other. This configuration is known as a trans configuration. So it's written the same way, but instead of it being cis 2-butene, it'll now be trans meaning different, to butene. There we go. So this is check. But, so 4 carbons, 1, 2, 3, 4, check. 2, yep, 2 trans, different sides. Yep, perfect. Moving on. Alright. This is going to be talking about reactions. So the following reactions are going to be all addition reactions. So this first kind of a reaction is called a halogenation, and the halogenation is pretty much you have an alkene. In this case, it is ethene, and it is being added with a halogen. So in this case, it's bromine. So we have ethene, and this one we already know is bromine. Pretty much what this will produce is going to be an alkyl halide. So this is how the reaction is going to take place. So we have our ethene, and there's a double bond, but we have 2 halogens. So what these halogens are going to do is they're going to be breaking down a bond. So it'll be like H, C. So instead of a double bond being present, it'll only be a single bond. That's what's going to happen here. Now, you're probably thinking, well, I mean, each of these carbons only has 3 bonds. They can form 4. Well, that's where the bromine comes in. Now what's going to happen is the bromine will bond with the carbon. This forms an alkyl halide. There's all single bonds, and here we have our halogens. So, yeah, this looks correct. Moving on. Now we have hydrogenation. Hydrogenation is just as the name suggests. We have it with hydrogen. So we have, once again, we have ethene and we have hydrogen. So this will produce an alkane, just a simple alkane. Going back to my pen. So this will be doing the exact same thing that the bromine did with our ethene back here. But in this case, we have hydrogens. So it'll be, the double bond will be broken down. So it'll be a single bond between these carbons. Let's draw our original first. Alright. Right over here. So now we have our hydrogens taking over here. There we go. Now we have our hydrogens. And it looks correct. So this is hydrogenation, and we have an alkene that is produced. In this case, it is ethane. Sorry. There's 1 carbon, 2 carbons, so it's eth, and then there's a single bond between them. So it's this ethane. Hydrohalogenation, which is just this is propene in this case, which is our alkene here. You write this down. Propene. Remember, we don't have to write any number because we know it's at number 1. So we have propene here, and this is being reacted with hydrogen bromide, so HBr over here. And what this is going to produce is going to be producing an alkyl halide. So this is what it's going to look like after the reaction. My pen out. Alright, so it's going to be H. Should I write the? I'll write the H. H. C. Then we have our S2 hydrogen, so we have our second hydrogen. Then now, instead of the double bond, only a single bond. CH, right over here. Then what we have is a CH3. Now, this one can fit one more bond, and this one can fit one more bond as well. So we have HBr, so it'll be hydrogen here and bromine here. Oh, whoops, forgot to color code it with red. No worries. Here we have our hydrogen, and here we have our bromine. And our double bond has been broken. So here is an alkane, an alkyl halide with bromine. This looks correct. Yes, it does. Moving on. Hydration. Just as the name suggests, it's with water. So an alkene with water. In this case, we have propene, once again, with water. And this will produce an alcohol. But keep in mind, an acid must be in presence. So let's say we'll take, sulfuric acid. Add in the aqueous. Now we have our sulfuric acid acting as a catalyst. Go back. Black pen. Yep, perfect. All right. So what this will produce is it will produce an alcohol. And here's what's going to happen. So we have a double bond here. Once again, the double bond will be broken. So we have a CH2, which is what it originally was. And then instead of the double bond, there will be a single bond now. So it'll be a CH, and then we will have another CH3 over here. Now there's 2 hydrogens and an oxygen. So what's going to happen is there will be 1 hydrogen over here, turning this. Oh, whoops. Where's my eraser? Alright. So this will be turning into a CH3. Turning into a CH3. This is now stable, so we have a CH3 over here. And we have an OH left over. Now, this guy needs another bond, so we have our OH over here. Perfect. So naming alcohols now. 1, 2, 3, prop. The alcohol is in the second carbon, so it'll be 2-propanol. And this is about it for alkenes. This concludes the video. If you need any more help, you can, replay this video. Go to any timestamp to check out what I did here. Also, once again, just quickly to review. Remember, you gotta find the longest chain, give the double bond the lowest number, mark down the substituents, put your equation together. Very simple. Double bonds. Once again, add in the A between the consonants. Depending on how many double bonds you have, it'll be either di, tri, or tetraene, and mark down where your double bonds are. Geometric isomers. Very, very simple. Same side is cis, different sides is trans. And we have our reactions: halogenation, hydrogenation, hydrohalogenation, and hydration. If you need any further help with these reactions, just play the video back and watch it again. Thank you for watching, and I really hope this video helped you. Have a good day.